Hello, in this video we're going to be talking about eigenvectors and eigenvalues. So to start out with, we have a definition. So T here is a linear transformation between V and V. So these two have to be the same in order for this definition to make sense. We say a vector V in the vector space that we're looking at is called an eigenvector with corresponding eigenvalue lambda if the vector is not zero, so the vector is not allowed to be zero, and the main equation that we want to have satisfied is that applying t to the vector is the same as scaling the vector by lambda. So t specifically when applied to the vector v acts like it's just scaling it out. Okay. So the scaling could be literally stretching it out, it could be compressing it, and it could be either of those two things combined with flipping it over. Okay? It could also be doing nothing if lambda is equal to 1. Then it's just t of v equals v, and that's totally fine, still satisfies this definition. So one thing I want to note before moving on to an example is that I said lambda is a real number here, but we also might want to consider complex numbers. Okay? And normally when I say we can replace R by C, I mean complex vector spaces are a thing. And everything that we do for real numbers also works in the complex case. But here I mean something slightly different. Here I mean even if V is a real vector space, it still will be useful to consider complex values for lambda. So even when V is real, we still want to look at complex eigenvalues. The main place where this might make sense is when V is Rn, and we can just pretend that we're looking at complex coordinates instead of real coordinates. Okay, so now we're going to look at this sort of abstract example. And what it says is we're taking a transformation from the set of 2-degree polynomials, or at most degree 2 polynomials, to itself. And the transformation is take the derivative of the polynomial and then multiply by x minus 1. And just to note, if you do this in the wrong order, if you multiply by x minus 1 and then take a derivative, you're going to get something completely different. So don't do that. Do it in this order. And I'll leave it to you to check that that is linear, but it is. And now let's plug in some polynomials into this transformation and see what happens. So the first polynomial I'm going to plug in is p equals 3. And so the transformation applied to the polynomial 3 is x minus 1 times the derivative of 3. So the derivative of 3 is 0 because 3 is a constant. Okay. And that is simply just 0. Right? X minus 1 times 0 is 0. And having a 0 here might initially look like a problem, but remember the thing that's not allowed to be 0 is the original vector that we have plugged into here. It's okay to get a 0 out here. What does it mean to have a 0 out there? Well, the idea is that I want to rewrite this in the format that looks like a number, in this case 0, times the original vector that I plugged in, which is the polynomial 3. Okay? 0 is equal to 0 times 3. And so we have here lambda is 0, and the vector that we plugged in is 3. So p is not allowed to be 0, but lambda is allowed to be 0. There's nothing wrong with having lambda be 0 here. So 3 is an eigenvector of this transformation t with a corresponding eigenvalue 0. Okay. Now we're going to look at x minus 1. See what happens when we plug in x minus 1. So I want to do x minus 1 times the derivative of x minus 1, which I'm just going to write down. Derivative of x minus 1 is just 1. X minus 1 times 1 is 1. But really I want to write this as 1 times x minus 1 anyway, because I want to think about this as a number times the original polynomial that we had. And so here we're getting a lambda value of 1. So this transformation T has an eigenvalue 0. It also has an eigenvalue 1 corresponding to different vectors. Okay? Just to note, whenever you take an eigenvector corresponding to a particular eigenvalue, say in this case 1, and you scale the eigenvector by a certain amount, then what you're going to get, so I'm going to just scale this by a factor of 5. So x minus 1 times 5 is 5x minus 5. And when we do that, because scalars can be pulled out of linear transformations, what we're going to get is x minus 1, the derivative of this is 5, and then we can rewrite that as 5x minus 5, or in other words, oh, I realize I made a typo here. I'm just going to leave it at that. I had equal to 1 here. That was nonsense. I'm not sure why I wrote that. So this right here is 5 times x minus 1. Oh. Let's write this the way I meant to write it. All right, so 1 times the original. So again, we get lambda equals 1. And that will always work. If you take an eigenvector and scale it by any constant, you end up seeing that it is also an eigenvector with the exact same eigenvalue. And you can see that that 5 in there could just be pulled out. T of 5 times v is the same as 5 times t of v, because t is linear. Okay. Also, lambda times 5v is the same as 5 times lambda times v, right? There's no reason that the lambda and the 5 can't commute. And so a 5 can come out of here, and a 5 can transfer past the lambda. Either one of those things is going to say that if you have t of t of 5 times v, it's still going to be lambda times 5v. Okay? So any scalar times an eigenvector is still an eigenvector with the exact same eigenvalue. Okay, so these two were a bit simple, or at least they look simple. They have lambda equals 0 and lambda equals 1. This last one is a bit less trivial, but I will point out there is some nice non-linear algebra going on here. I started out with a constant. Remember, any scalar would also work. So I could scale this to, say, 1, and this would still be an eigenvector. So 1, x minus 1, and this is x minus 1 squared. So x minus 1 to the 0, x minus 1 to the first power, x minus 1 squared. These are all eigenvectors for this transformation, and that is not a coincidence. But we don't need to worry about that for now. I'm just going to plug this in and see what happens. So we have x minus 1 times the derivative of this, which is 2x minus 2. All right, so I am now going to multiply this out. So it's going to give us 2x squared minus 2x minus 2x, and then plus 2, and that is 2x squared minus 4x plus 2, which can be written as 2 times x squared minus 2x plus 1. So it's 2 times our original polynomial, which means here we have an eigenvalue of 2 corresponding to this eigenvector. Okay? So next up, we're going to be looking at matrices and eigenvectors and eigenvalues of matrices. The definition I have written here is equivalent to this definition, but I decided to write it in a slightly different way just for variety, but they mean the same thing. So A is an n by n matrix. So recall that these two vector spaces need to be the same, and in terms of what that means for a matrix, because matrices correspond to transformations between Rn and Rm. Saying that those two are the same is the same thing as saying that n is equal to m. So the number of rows has to be equal to the number of columns in order for this to have an eigenvalue, or for it to make sense to talk about what it means for it to have an eigenvalue. So we say that lambda is an eigenvalue if the equation ax equals lambda times x, which is the same thing as this equation right here, t of v equals lambda times v, if this equation has a non-trivial solution. So saying that the solution is non-trivial means that there is a non-zero vector x such that this equation holds. So it's the same thing as this first condition here. The vector, which is called the eigenvector, is not allowed to be 0. Okay, that's exactly what this last sentence says. So we have an example now of a concrete matrix and a corresponding eigenvector. Okay, so now let's just plug this in, see what we get. A times x, -1, -2, 3, 4, times the vector x. Okay, so the first entry, the top entry, is going to be -1 times 2 plus -2 times -3. And the bottom entry is going to be 3 times 2 plus 4 times -3. All right, so when we simplify that, -2 plus 6 is 4, and 6 minus 12 is -6. And we can see that this is exactly twice that. So x is therefore an eigenvector, and the eigenvalue associated to it is 2. So how might we go about finding what these eigenvectors and eigenvalues are given a particular matrix? Well, finding an eigenvector or eigenvalue amounts to solving this equation. And it turns out the easiest thing to do is to solve for lambda first. So we want to find the eigenvalue before we try to figure out what the eigenvectors are. Okay? So solving this equation can be done by doing a little bit of manipulation. Okay? So we want to rewrite this, first of all. This is the same thing as saying a times the vector x is equal to lambda times the identity times x. Okay, so I is just the identity matrix, and specifically it's the nth identity matrix, right? The n by n identity matrix. So we're always allowed to put that in there because it doesn't change it, right? Identity times a vector is just the vector itself. It doesn't change the vector. So once we have this actually makes it a little bit easier to work with, because lambda times the identity can now be thought of as a matrix. So in other words, we can put that in and not change it. And then we can use the associative property, to say that this is the same thing as lambda times in, this matrix, then times the vector x. And now what we're doing is we're solving this matrix times x is equal to this matrix times x. Okay? And we can subtract everything to the left-hand side. That's the same thing as saying ax minus lambda times the identity times x is equal to the 0 vector. All right, so now we have this x in both of these terms, so we can factor that out to the right side. So what we're left with is a minus lambda times the identity. So this is now one matrix times x equals 0. And as long as we can write down what that matrix is, then we can solve that matrix times x equals 0 with our standard methods. So what does this matrix look like? Well, let's do it for this example right here. So n is equal to 2. Our matrix A is -1, -2, 3, 4. And when we subtract off lambda, I'm going to leave it as a lambda, even though I know lambda will end up being 2. Remember, our goal is to find lambda, times this 2 by 2 identity matrix. And I want to solve this equals 0. In other words, equals 0, 0. All right, so we're trying to find the value of lambda that makes this true. Okay. Oh, sorry. Forgot the x. Okay, so I'm going to write this as one 2 by 2 matrix instead of the difference of two 2 by 2 matrices is one scaled. So lambda can just be multiplied by all these entries. We get lambda 0, 0, lambda. And when I subtract this off, it's just going to subtract off lambda from these two diagonal entries. So what we're going to end up with is -1 minus lambda. And in this other diagonal entry, we're going to have 4 minus lambda. And these two are just minus 0 over here, so they're not going to change. So we have this times our vector x, whatever that may be, is equal to 0. And finding lambda here is the same thing as finding a matrix of this format such that I have a non-trivial solution to matrix times x equals 0. Now, you may recall that in order for this to happen, this matrix has to not be invertible. Okay? So if I had an invertible matrix over here, I could take the inverse of it and multiply both sides of this equation by the inverse of this matrix, and I would get that x is equal to the inverse of this times 0, which must be 0. Therefore, x is 0. And I need x to be non-trivial. Okay, so I need a non-trivial solution to this, so x is not allowed to be 0, therefore this matrix cannot be invertible. Okay? And it turns out if this matrix is not invertible, then there will be a solution to this. So the only thing we really care about is this matrix is not allowed to be invertible. So the way we're going to deal with that is we're going to take the determinant of this and set it equal to 0. So recall one of the nice properties of determinants is that if the determinant is 0, then the matrix is not invertible. And that is actually an if and only if. So if A is an n by n matrix, then det of A not equal to 0 if and only if A is invertible. Alright, so we know that A cannot be invertible. So we want to try to say that this determinant of this matrix is 0. So let's take the determinant of it. So the determinant of this is the product of these two minus the product of these two. Okay, just remember that determinants get a bit harder as you increase the size of the matrix, but they're still doable. If the matrix is too big, remember you can always use a computer to do that for you. Okay, so we have -1 times -4, sorry, -1 times +4, plus -1 times negative lambda, plus negative lambda times +4, plus negative lambda times negative lambda. Okay, and this is minus -6. All right, combining like terms, we're going to get lambda squared minus 3 lambda, and then -4 and +6 make +2. So what we have here is something called the characteristic polynomial. And in general, the characteristic equation says that this determinant, which is this, when you set it equal to 0, is going to give you an equation that every eigenvalue will satisfy. Okay, so setting the determinant equal to 0, remember, is the same thing as saying our matrix A is not invertible, which is the same thing as saying that this equal to 0 has a solution, which is what we're looking for. So we don't know what that solution is, but at least it has a solution. So we're finding lambda first. So what lambda will make this equal to 0? Well, we have to factor this. So if lambda squared minus 3 times lambda plus 2 is equal to 0, then let's see, we're going to get lambda minus 1 times lambda minus 2 equals 0, and so we're going to get lambda equals 1 and lambda equals 2. Okay, so we have two different values of lambda that will make this work. Remember that lambda equals 2 we knew worked because we actually knew the corresponding eigenvector for it. But this is how you would find that. Once you have the lambda, then you can go back and find the corresponding eigenvector by plugging that lambda in. So let's do that now. So we've already found the eigenvalue lambda equals 2. Now we're going to find the vector. Okay. So the eigenvector is just going to come from taking this right here, times x equal to 0, and solving. So remember, a minus lambda I times x equals 0. And we know what lambda is now. So this is lambda equals 2 is going to give us -1 minus 2, 3, -2, and then 4 minus 2. Okay, and I'm solving this equal to 0, so I'm just going to go ahead and augment this right now. And that's the same thing as saying -1 minus 2 is -3, -2, 3, and 2. Whatever matrix you get here, remember, is not going to be invertible. We are trying to find essentially the null space of this. Okay, so we're trying to find the null space of this matrix A minus lambda I, which is why we're setting equals 0, and we expect to find a non-trivial solution. So in a 2 by 2 case, you're always going to get that these two rows or these two columns are linearly dependent. And in general, there's going to be some dependency among all the rows or all the columns whenever you have a non-invertible matrix. That's one of the parts of the invertible matrix theorem. So in this case, solving this is going to tell us that, let's see, I'm going to call this A and B. We're going to get that 3A plus 2B is equal to 0. In other words, A is equal to negative 2B over 3. Okay, so if we wanted to find a vector AB, what we would have to do is pick a B, and I'm just for convenience, I'm going to pick 3 for my B. And then we can figure out what A is based on that by doing B times negative 2/3. So 3 times negative 2/3 is negative 2. And this is an eigenvector corresponding to the eigenvalue lambda equals 2. Okay, notice that this isn't the one that I found over here, but that's fine. This is a scalar multiple of it. That will not always be the case, but in the 2 by 2 case, it's usually going to happen unless your matrix is very silly. Thank you for watching.